All right, yep.
All right, hello, welcome back to another Mathcounts video. Today we're gonna continue 2015 Nationals. So we left off on number 20. For a particular sequence, the first term, A1, is 1, and for every term thereafter, the value of the nth term is given by A sub n equals A sub n minus 1 plus 2 times n. What is the value of A100? All right, well, A1 is 1, right? So by that equation, A2 will equal A1 plus 2 times 2, because in this case n is 2. So then and A3 will equal A2 plus 2 times 3, because in this case n is 3. So we can just substitute A2 in here, and we will get A1 plus 2 times 2 plus 2 times 3 for A3, right? And then this pattern will just keep on going. So that A100 will equal all this plus all the way to 2 times 100. So yeah, then we just have this sum, and it's not hard at all. This is just an arithmetic sequence. So the sum of 2 times all this to 100 is just 2 times the sum of 2 plus 3 plus all the way to 100, which is just an arithmetic sequence. So then that would just be 102 times 99 over 2. We're going to multiply by 2 because all of them are being multiplied by 2, and we add 1. So the 2's cancel, so then we just have 102 times 99, which will just be 10200 minus wait. It would just be 1020 minus 102 plus 1. So then it's just 1020 minus 101. So then it's just 10099. And we're on number 20. Yeah, that's our answer. Number 21, if f of x equals negative x if x is less than 0, and negative x squared if x is greater than or equal to 0, and f of x is 4, what is the value of x? All right, so we should kind of work backwards on this. You have f of x, and it equals 4. So we'll look at the two cases of if f of x is less than 0, or if f of x is greater than or equal to 0. So in this case, this last f will apply the negative x onto f of x. So then it's saying negative f of x equals 4, or just f of x equals negative 4. And then we can just apply the same thing. So now we'll set conditions onto f of x. So this is a condition of if f of x is less than 0, or if f of x is greater than or equal to 0. So in this case, we will apply the negative x on this f. So then we will have f of x equals 4. So f of x equals 4, when is this possible? Well, it's possible when x equals negative 4, because then it's negative and it applies the negative to get 4. And it's also possible when, x equals 4, because it's positive, so, not 4, sorry. When x equals positive 2, because it's positive, and we'll apply this and we'll get negative 4. Oh wait, actually, no, this isn't possible. Yeah, okay, you can't have any positive solutions because it will always be negative, but we want it to have a positive solution. Okay, so we get x equals negative 4 for this, so we should see if it works. So does it work for the f of x is less than 0 condition? No, it doesn't, right? Because this is 4. which is not less than 0, so this condition just does not work. So maybe we should have seen that beforehand, and then we could have just applied that. So yeah. All right, f of x is greater than or equal to 0. So then this second half will apply the negative x squared onto it. So then it's saying f of x squared equals what? Equals 4. So then f of x can equal 2 or negative 2. But f of x has to be greater than or equal to 0 from this condition, right? So then f of x just equals 2. All right, if f of x equals 2, then what solutions do we have? Well, we just have x equals negative 2 because it's going to be negative. We apply the negative, we get positive 2. And we can't have any positive solutions because if they're positive, then this will be negative, and then we can't get anything positive. So let's see if this x equals negative 2 works out. So f of x will equal to f of x will equal oh yeah, this will all work because f of x equals negative 4, and it does satisfy our conditions here, right? So yeah, this should work. X equals negative 2 should be one of our solutions. And now we look at f of x is greater than or equal to 0. So in this case, the third f will apply the negative x squared onto it. So then we will have f of x squared will equal negative 4. But this is not possible, right? Especially, I mean, this is just you can't square a real number to get a negative number. So then our only solution should be x equals negative 2. And it just asks what is the value of x. So we're always supposed to have one solution. So yeah, that's our solution. Our answer is negative 2. You can also do this in other ways. So one thing you can notice is that these just talk about whether x is negative or non-negative, right? And if it's negative, it will negative it, right? And if you negative a negative, it will turn out to be a positive. So if you have f of a negative number, it will turn it into a positive. And if you have a positive number or non-negative number, it will make it back negative, right? Because something squared will always be positive, but especially because this is positive. But yeah, so basically, the f's will change the sign of the x every time you apply f, which means what? Which means that f of x must be negative because f of that will be positive. And we said every time you f something, it will change the sign of it. So likewise, f of x must be positive. So then x must be negative. All right, and so then we know x is negative. That might help you a little bit. One thing you can also notice is that whenever you change a positive into a negative, you have a square on it, and otherwise the magnitude is unchanged. So if you look on our thing here, so f of x will be positive because it is equal to 4. Hold on. Okay, so f of x will be equal to positive 4. Okay, so every time you change a positive number into a negative number, it applies the square, right? And otherwise the magnitude is unchanged. So how many times do we change a positive into a negative? Well, only one time here, right? Which means what? Which means the 4 magnitude as we go down here will be unchanged except for this one square in here, right? But this square is going up. So if we're going back down, we're going to square root the 4 one time, right? So then that tells us that the magnitude of our x here will have to be 2. And we know its sign has to be negative, right? So that means our solution has to be x equals negative 2. So if you notice that, that might be a slightly faster way to do it. Do you have anything to add on to that, Bill?
I mean, you went over like both ways to do it, so I mean, yeah, when you're doing this, I think the faster would just be noticing that, there's only one of them turns the number from negative to positive, and then one of them turns the number from positive to negative. And then just seeing that the number will be squared once, and also that it's gonna have to be what negative. So it's pretty easy to just arrive at the point that it's negative too.
Yeah, okay. All right. Number 22. If six people randomly sit down at a table with six chairs, they do not notice that there are name tags marking the assigned seats, what is the probability that exactly three of them will sit in the seat he or she was assigned? Express your answer as a common fraction. Okay, so basically, we're gonna have just, I mean, you can think of the chairs as labeled 1, 2, 3, 4, 5, 6. And then we have a random assigning of 1, 2, 3, 4, 5, 6 to each of these numbers. And we want to find the probability that exactly three of the numbers match. All right, so how are we going to do this? Um, all right, so we can think of the number of combinations or number of permutations that this condition has, and then we put it over the total number of conditions that this has in total, which is just the total number of ways like you can assign people to seats, right? So let's find the total number of ways you could do that first. I mean, that's going to be pretty easy. It's just going to be, so like we have the people 1, 2, 3, 4, 5, 6 as well. Maybe we should do letters just so we can do like capital and lowercase. So the seats can be the capital letters and the people can be the lowercase letters. So we can specify it a bit better. All right. So we assign the lowercase letters to the seats. All right. So so for like this person, we can assign them to any seat. So they can be assigned to any seat. So that's gonna be 6 ways. And then the next person can be assigned to any other seat. So it's just gonna be like that, and it's just gonna be 6 factorial. And then we think, will that be overcounting anything? Well, no, right? Because each of these will be a different condition because like each of these, if A is assigned a different seed, all of those will be different conditions no matter what. So yeah, our total number of ways we can assign people will be 6 factorial. Now we just need to find the total number of ways that we can assign the 6 people while having 3 of them matching. And then we put that over our total number of ways, which is 6 factorial, and that will be our probability. So yeah, so how many ways can we assign them to have 3 people exactly matching? Well, without loss of generality, we can assume, well, okay, um, sure. Uh, um, okay, so okay, yeah, we could do it like this. So we have the people A, B, C, D, E, F, right? So 3 of these people are going to match. So we can choose which 3 people are going to match by doing 6 choose 3, right? Because we have 6 people and we need to choose 3 people that will match. Okay, so we choose 3 people, and now without loss of generality, we can assume that they were ABC. Okay, and then so they have to be matching on their seats, so we can't do anything about that. So there's nothing else to that. But the FED, they can be sorted in any way such that none of them will match with their seat. So how many ways are there for you to do that? Well, you can just think about it. If you have FED like this, then how can you do it? Well, F can't be here, so maybe it can be here. Well, then E can be here or here, but if it's here, then D can't be there. So E has to be there and D has to be there. And then we look at the case where F is here. Well, then there's just one case like that. And there's no other cases. The other cases will have at least one person matching. So we only have two cases for the other people. And so our total number of cases for this will just be 2 times 6 choose 3. So then our probability will just be 2 times 6 choose 3 over 6 factorial. So 6 choose 3 will just be 6 factorial over 3 factorial over 3 factorial times 2. And over 6 factorial, so we can cancel out the 6 factorials, that will just be 2 over 3 factorial and 3 factorial, and 3 factorial is just 6. So then this is just 118. We're on number 22, so our answer is, 118. Anything you want to add on to that, Bill?
I mean, not really. I mean, that's probably the easiest way to solve the problem. So yeah, there's not really anything to add.
All right. Oh wow, I took up a lot of space already. I don't think I zoomed in enough. Oops. All right, whatever. Okay. All right. Number 23. A sequence is unimodal if A1 is less than A2 is less than all the way to A sub k minus 1, and that is less than A sub k. And then that is greater than A sub k plus 1, and keep on going greater all the way to A sub n. For some value of k such that 1 is less than k is less than n. So k is somewhere between 1 and n, but it is not equal to 1 and n. How many permutations of the numbers 1 through 8 form a unimodal sequence? So basically, we have to have the sequence increasing to some number, and then it has to be decreasing down. How do I take this? Okay, so well, we could just think of it as increasing from both sides. And so like this number right here, we're increasing from everywhere, right? So then this number has to be our maximum. So it has to be 8. And in addition, this will be our a sub k, right? We can see that a sub k is our maximum here. And it says that 1 is less than k is less than n, so k can be anywhere except equaling 1 or n. So basically it's saying that 8 can't be the first or the last number in our sequence. All right. So then maybe we can just separate it into casework. So we look at where 8 is in the second position, the third position, and the fourth position. And then we can just use pi symmetry and multiply by 2 for the other side, right? Okay, so let's do that. So I'll notate this as 8 in 2, 8 in 3, and 8 in 4. And then we have to remember to multiply by this by 2 to mirror the other side. So also goes times 2. All right, so if our 8 is in the second position, this spot has to be less than 8, right? But every number that we have will be less than 8, right? So there's essentially no condition on this number. It can be whatever. And then we have the other 6 numbers there, right? And the condition on these numbers is that it has to go decreasing that way, right? So then what cases do we have? Well, we can have 7, 6, 5 all the way down to 2, and we can have 1 there, right? So that's one of our cases. And then all of the other cases, we have to have 1 in this position, right? So like either the least number or the second least number has to be in this position, right? Because either the least number is here or the least number is there, and then the second least number has to be there, right? Okay, so if the second least number is there, that means 2 is there, And the only way you can have 2 in there is if you have 7 all the way to 2 and you have 1 there. Okay. So now we look at the case where we have 1 here. So then what can happen? Well, these numbers have to be decreasing and we can have any number in here. So I mean basically it's just like we have the numbers 2 through 7 and we put it in there except we take one out. And the one that we take out is the one that we put there. And all of those will be cases, right? So then how many cases are in there? Well, it's going to be 6, right? Because we have 6 of those numbers and we can take any of them out. So we have 6 takeouts, so that's going to be 6 cases. So we're going to have 7 cases for that. All right, so what happens if 8 is in the third position, right? Then all of these have to be decreasing and these have to be decreasing as well. Well, this making it decreasing isn't actually like a huge constraint at all, right? You could choose like any 2 numbers and you could just always put them in a way so that they're decreasing. Essentially, the decreasing just says that you only have 1 case on this. Like once you choose your 2 numbers, then you only have 1 case on that. But you can choose any 2 numbers to be on here, right? So yeah, you could just think of it like that. So we have 7 numbers. We have 7 numbers, and we can choose 2 of them to go in these 2 blanks, right? And once we have those 2 numbers, then they only have 1 case for them to go into, right? So then all of our cases have to come from 7 choose 2, and that's also because once we choose the 2 numbers, the 5 numbers that we're left with have to go in 1 exact position, right? So okay, so yeah, think of it like this: we have 7 numbers, okay? We choose 2 of them, and we will be left with 5, okay? And then the 2 of them have only 1 position to go in here, and the 5 other ones only have 1 position to go in here, right? Which means that our total number of combinations will just be 7 choose 2. So this is just 7 factorial over 2 factorial over 5 factorial. So that's just 7 times 6 over 2. That's just 21. And likewise, this one will be just 7 choose 3, right? Because it's like the same thing as this one. We're just choosing 3 numbers to go in these blanks out of the 7 of the numbers that we have. So this will be 7 choose 3. So this is just what 7 times 6 times 5 over 6, which is just 35. And then we can just add these, which will be 53. And then we just need to multiply by 2. Yep, which will just be 106. Uh-oh. This should be 63. Yeah, it should be 63. So yeah, then this is 126. Yeah, it's 126. Yeah, also one thing you might notice is that here we have 7 choose 1 plus 7 choose 2 plus 7 choose 3 for 8 in the first, or 8 in the second, third, and fourth position, right? And then the others will be likewise 7 choose 4, 7 choose 5, whoops, 7 choose 5, and 7 choose 6, right? And so we can see our double working out because of the mirror, and like the 7 choose 1 equals the 7 choose 6, right? And the 7 choose 2 equaling the 7 choose 5. So you can see so you can also see like in here that like where the times 2 comes from. And also I don't know if this really saves you some time, but you could also use the fact that if you have like if you have n choose 0 plus n choose 1 plus dot 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 all the way to n choose n, then this sum will equal 2 to the n. So this is like what we have here, except we're missing the 7 choose 0 and the 7 choose 7 choose at or 7 choose 7, right? And we're missing that actually because the 8 can't be in the first or the last position. So yeah, so this sum will equal 7 to the n minus are 7 choose 0 and 7 choose 7, right? But 7 choose 0 and 7 choose 7 are just 1. So then we just need to multiply, or we just need to minus that by 2. That's totally bad. I meant to write 2 to the 7th power. Okay, so yeah, our answer of this is just going to be 2 to the 7th power minus 2, which is just 128 minus 2, which is 126, as we got before. All right, anything you want to add on to that, Bill?
I think you explained it pretty well. Uh, I mean, yes, just this is basically you're just choosing the numbers. When you after you choose the numbers will arrange themselves, so there's not really any point in like worrying about the order of the numbers. It's just choosing them. Other than that,
Yeah,
yeah.
that's one thing to notice. It's just you just have to choose them. All right, let's move on. Number 24. How many ordered pairs of real numbers x, y satisfy exactly two of these equations? So we have some equations here. You can notice that they are circle equations. These two are circle equations, and this one is just a line. All right, um, so basically we're just looking for solutions that satisfy two of them, but not all three of them. So one way you could do it is you could graph this like by hand because you don't have calculators on screen. You could graph the two circles and graph the line, but you have to make sure your graph is really well drawn um, in like to scale. So then you can see if like an intersection is actually like one intersection instead of like three really close intersections. And then yeah, yeah, you can't graph it. So like if you graph it, you could do it by counting where you have two graphs intersecting, but not all three, and then that will be your answer. But again, you have to be careful on that because you could draw it like really close where it looks like I don't know. You just have to draw it well, or else it could fail. Like some might not cross, or cross more than they're supposed to, and whatnot. Right? Okay. Um, so yeah, you can graph it, but I'm not going to graph it. I think it might be better for me just to solve it, and I don't know. I don't like graphing that much. But if you like graphing, you could definitely do it by graphing. All right, but I'll just solve it by solving the equations. So you know we can just solve for these. It's not that bad. So let's just start with the first two equations. Um, so we can just subtract them. So so we're gonna cancel out the x squares and y squares. So then we're gonna have negative 6x plus 9 minus 8x minus 16. And the y squares are going to cancel, and then we're going to have negative 8y plus 16, and then this is going to be negative 6y, but we're going to minus it, so it's going to be 6y, and we're going to have positive 9, so we're going to minus 9, and 25 minus 25 is 0. So then we have negative 14x, these 16s cancel, these 9s cancel. We have negative 14x minus 2y equals 0. So then we have negative 2y equals 14x, or y equals 7x. Okay, so our solutions of those two equations will land on the line y equals 7x. So we can plug this back in into the what or any one of these equations to find what those solutions are. So we can just plug it into this one. So we're going to have 7x minus 3 squared equals 25. So we're going to have x squared plus 8x plus 16 plus 49x squared minus 42x plus 9 equals 25. Maybe it's actually better and faster to do it by graphing. Yeah, it's probably a lot faster actually. So yeah, maybe that is a better method. So all right. So wait, Bill, do you know if they give you like protractors or something on screen
Ooh,
so like you can draw circles and stuff?
I know it's allowed for AMC.
AMC? Yeah.
Um, I'm not sure.
Yeah, I'm not sure.
I can check.
Okay, yeah. If you do this, there's these 25s cancel. So then you're left with 50x squared minus 34x equals 0. Okay, so then you're left with two solutions. It's x equals 0 and x equals 34 over 50. So this is just 17 over 25. All right.
I don't think you are allowed a protractor.
Then I know. And you just need really good drawing skills, I guess. Um, okay, so these are our solutions of x for these two equations, and we don't have to solve for y here, right? Because we just want to see how many solutions we have, and not anything about the y values. Um, so like basically like if we look at these two equations and we have some x values, and we look at these two equations, and like one of them has the same x value, then those x values have to give the same y value, right? Because they use like one of the same equation, right? So basically, we just need to keep track of the x values and not the y values, and then we can see just how many we have. You can calculate the y values if you want to, but it's just unnecessary and it'll waste your time. So yeah. Okay, now let's do the first and third. So we can just substitute y for negative 6x. So then we'll have x squared minus 6x plus 9 plus 36x squared plus 16 plus what 48x equals 25. Um, all right, and then we have 37x squared. 9, 16, 25 cancels out, and they'll cancel every time actually. Um, plus 42x equals 0. So then we just have one, or no, okay, yeah, we have x equals 0 and x equals what? Negative 42 over 37. But the x equals 0 is already counted for, right? We can still keep it, but we need to make sure we don't count it in our count. Or more than once this way. Okay. Lastly, we have the second equation and the last equation. Just plug in y equals negative 6x. Then we have x squared plus 8x. And the 4, the negative 3, and the 25 will cancel out. So we just have plus 36x squared. And then we have plus 36x equals 0. Then we have 37x squared plus 44x equals 0. Okay, then we have x equals 0 and x equals negative 44 over 37. All right. So it looks like we have four distinct solutions here. X equals 0 and x equals the other stuff. No, I did something wrong. Probably just did some algebra wrong. Uh, oh, y equals negative 7x. I forgot that negative there. Okay, so then this will be positive 42x. And then when you add those, that will be 50x. So then we have 50x squared plus 50x equals 0. This still gives us 4. We have x equals 0 and x equals negative 1. Uh, Wait, do you remember what x's we got when you were doing this?
Oh, no, not really. I
Uh,
mean, x equals 0 would definitely be one. Oh, x equals 0 would be a point where all three of them would be intersecting.
yeah. Um, you guys did the algebra wrong here. Yeah, you have to be careful on algebra. Um, yeah, and I always make mistakes like this. I don't see anything wrong here. Do you think you can put it into your TI and see what you get?
Yeah, sure.
Can you still hear me?
Yes. So I got, so
Uh,
for the top two equations, I got x equals negative
I
1 and
can't
x
hear you
equals
now.
0. No
Wait,
signal.
say something. Oh, okay, I can hear you now.
Mhm.
Can you hear me?
Yes.
Okay.
Okay, so do you want to know the numbers?
Yeah.
Okay, do you want to know all of them?
Yeah.
Okay. So for the top two equations, it was x equals 1 and x equals 0.
X equals 1.
X equals negative 1, sorry.
Oh, okay.
For the for the first and third equation, it was x equals negative 42/37 and x equals 0.
Okay.
For the second and third equation, it was x equals negative 44/37 and x equals 0.
Wait, yeah, that's what I got.
Yeah.
I'm so
Did you
bad.
count? What did you
We
count?
don't count zero at all
Yeah, yeah.
because,
I was about to say, did you count
oh,
0?
yeah,
Because we don't. It's only two, exactly two of these equations.
yeah, yeah. So then, yeah. Okay,
Yeah.
so zero shows up in all of them, right? So, it satisfies all three equations, so you don't want to count zero at all. I accidentally counted zero. So yeah, you have to be careful on that. So then you just have like one solution for every pair, -1, -42/37, so -44/37. So then you just have three. Yeah, three. Um, should I also try to draw it to see if that will work? That's likely not going to go well though.
If you draw it, I guess you can like visualize it, but you would have to draw it like a very accurate graph, I think.
Yeah.
But I think it's definitely possible to like visualize it that way.
Hmm.
Because I mean, it's not asking you to like get the exact number. I think drawing it would help. You would just have to, get the important points right.
Yeah, let me try it. So, so what you should notice is that 0, 0 is a solution to both of the circles. So, and also the line. So when you graph them, they should all be crossing 0, 0. Alright, so let's graph the circles first. So we're gonna be at 4, 3. Okay, so it's gonna go here. Let's just. Alright, that's interesting. Okay. And then we have -4, 3, so right here. And it's just gonna be like this. It's just gonna be the opposite of that. And then we have -6x. Hmm. Yeah, okay, so well it's likely going to be like this. Whoops. So it's likely gonna touch the circle somewhere here. And then so we're gonna go like this. And okay. So maybe like this. So okay, so we don't count that solution, but we will count this one, and this one. And yeah, that's all you have here. So yeah, I yeah, I didn't draw this extremely well, but I still got it. So I guess it doesn't have to be too accurate. I just think you just have to have this like -6x line within this circle. You don't want it outside of it. If you had it outside of it, then you would get the wrong answer. But as long as you had it like inside and not like crossing with this point, then your graph should have been pretty safe to get the answer. So really not that bad of a graph. So maybe you could have like tested graphing at the start and see if there's like small mistakes that you can make, or it's generally like an estimation that you can make. Um, so then like if you think it's pretty good, or like that you can't really like fail on it, then you can just go ahead and go with it to save like a decent amount of time. But if you think like it's really close and like you just think I don't know, some stuff like it's really hard to draw and stuff, then you can just try to solve it. Um, but I do think graphing would actually be the better way to do this. It's a lot faster and this is pretty easy to see, and there's not much room for mistake here. All right, anything you want to add on to that, Bill?
Um, I guess not.
Um,
I guess you can also do this like if you're really wanting to like if you're really like crunching time, you can see that. Actually, would this even work?
no, I just
Yeah.
think drawing this would generally be the better way to do it. Like it saves you a lot of time, and like this is a really easy graph to do. Um, yeah. Um, the only way I can see you making a mistake here is if you have this line outside of this, right? But I mean, you can even think of it mathematically. Like this circle is going to be symmetrical about the line y equals x, right? Which means that the line like tangent right here, the instantaneous slope right here, is just the y equals negative x slope. So, so this slope is like only -1 here, right? But this slope is -6, so then it has to come in there. So, so even that you can think through, and it doesn't have to be like purely drawing and stuff. And I mean, and then these two circles are symmetrical about the y-axis, so that's easy. So you just know it's like that. And yeah, also, you just want to find the number of solutions there are, not like finding actually what they equal to. So then graphing is definitely valuable. All right, anything you want to say?
So, I mean, there's a sort of risky thing you can do, I guess, and that's just you can see that they all three of them intersect at 0, 0, and only at 0, 0. They all three of them intersect only at 0, 0. So you would just go. They probably. So you would just go like all of them will make six, and then take away three, and then get three. That's really risky. I don't do that. That was a bad idea.
Wait, what?
So
Wait, what?
like, there would be like six total solutions, right?
Yeah.
And then you see that all three of them intersect at 0, 0. So that takes away three of the solutions.
Like you can still just like
Yeah,
draw a
you
vague
can graph it.
diagram and
Yeah.
see it. Okay. Yeah. So um so I would say for problems like these that like ask you for like the number of solutions to something and not like finding the numbers, I would say test graphing, see if it's pretty good or like pretty bad. So if it's pretty good, you can just go with it and maybe like put a dash by it. So if you have extra time at the end, you can come back to it and just make sure that your graph was good and stuff, or like solve it actually. And if you think it's pretty bad, then you can just just go with solving it, and um vaguely drawing the graph shouldn't have taken you a bunch of time. So yeah. All right, let's move on. Um, I'll do it here, I guess. Right triangle ABC has side lengths AB equals 4 centimeters, BC equals 3 centimeters, and AC equals 5 centimeters. A is also a vertex of the square, and B and C lie on two sides of the square as shown. What is the area of the square? Express your answer as a common fraction. Okay, so we have a square. We have a triangle. A is on the corner of the square. Okay, not the best diagram. I'll redraw. It's more like this. Okay. A, B, C. AB is 4, BC is 3, and AC is 5. So we have a 3 for 5, and yeah, that's a right angle. Okay. And we want to find the area of the square. So essentially, we should try to find the side length of the square. Okay, so one thing we can do here is have the similar triangles of this triangle and this triangle. So if I label these points as like D and E, we can say that the triangle AEB is similar to the triangle BDC. So why can we do that? Um, well, we have this angle here, right? The complement of its angle will be this angle. So why? Well, these form a right angle. I mean, sorry, these form a right triangle. So then the sum of the angles have to be 180, right? So these two have to sum to 90. So these are complementary, right? But here on this side, this this has to be the same as that angle, right? This has to be the complementary or the complement of this angle, right? Because we have another 90-degree angle here, and all these angles have to sum to 180. And with the 90, then these two have to sum to 90, or these are complements, right? But we know that these are complements, right? So then these are equal, right? And by the same thing, this will be the two angle one. Okay, so then, we have just similar triangles by AAA. So then we can have this. Okay, so then one. Then we can just label any side as x. Have the side as x, and then we can figure out what this side will be by the Pythagorean theorem here, right? So it's going to be 16 minus x squared rooted. So this is going to be 16 minus x squared rooted. All right, and then let's say that this is y, and we can also put this as we could also put this as 9 minus y squared rooted. Okay, so from the similar triangles, we can make a ratio. We can say that x over root 16 minus x squared will be equal to y over root 9 minus y squared. Okay, but this is enough. This is not enough to solve for x or y, right? Because two variables, one equation. So we have to find another equation. Another equation we could do is we know that x is this entire side, so then x has to be the sum of y and root 16 minus x squared, right? So x equals y plus root 16 minus x squared from right there. All right, so then we can just actually I'll substitute y for x minus root 16 minus x squared. So that we can just solve for x, and that's really what we want, right? Solve for x, and then we just square it, and we get the area of the square. Okay, so we'll substitute what y is into our ratio. So it's going to look like this now. And y squared, that's not too nice actually. Yeah, that's kind of bad. All right, and then let's just cross multiply. This isn't a very nice algebra, I don't think. I thought we had better algebra when we solved this. Did we solve it this way?
Mm, did we? I honestly don't really remember. It was a while
Yeah,
ago. I don't really remember how we solved it.
I mean that's really like the only thing you can do here, right? So, but I don't remember our algebra being this bad. Oh, whatever. Let's just try to solve it. Okay. So we're gonna have this, and it's going to equal this times that. All right. So we need to multiply everything out. Okay. So this will be 9 minus x squared minus 2 root 16 minus x squared plus 16 minus x squared. And it will be equal to x times root 16 minus x squared minus 16 plus x squared. Okay? And then, alright, we can simplify this a little bit. We can cancel out the x squares. So then we have 9 plus 2 times root 16 minus x squared minus 16. Okay. I won't write that again. And then, this will be 2 root 16 minus x squared, minus 7. And then you don't really have much. Then you just need to get rid of the square root by like squaring both sides. Yeah. So okay, let's get rid of this x. So we can like cancel out these x's, and have this over x. So we'll have this. See what now we're squaring a trinomial. I definitely don't remember doing that.
Okay. Now check the answer real quick. Is it 409617?
Wait, what?
Never mind, it's not.
256 over 17.
Okay,
Oh,
so
do
I'm
you
on.
plug it into your TI?
Okay, no, I'm not, I didn't. So I'm onto something, but I'm just slightly off.
Oh, wait, what?
Okay,
Wait,
so
can you plug this into your TI and
okay,
see if you
so
get
no,
that?
I have a different way of doing it. I have a different way of doing it. I think it's better.
Oh, okay, okay.
Okay, so the bottom left triangle is similar with the top left triangle, right?
Oh, yeah.
And we can find proportions between them. We can find the
Oh,
proportion
why
to
did
those
I
two.
use?
It's 4 and
Okay,
3,
yeah,
right?
yeah, I know, yeah. Okay, yeah,
So
that was a big mistake.
you can use that to
Wait,
find.
wait, but also, if you didn't know that, this should also work, right?
I mean, but that's
Wait,
basically
okay.
brute forcing it,
Do you
basically.
think do you think you can put that into your TI actually?
I mean, I
I
can
don't know. I just
try,
want
but
to see
that's
this one.
basically just brute forcing it, I think.
Okay. Okay, but yeah, so it would be better to use the already there 4/3 ratio.
Yes.
Um, I mean that's just way better than having all the x's and y's, and so we get really bad stuff. But then we're like given some extraneous information, right? We actually have like more than we need. I don't know. Okay, whatever. Okay, so then uh uh then what? Then we can say x over y equals
Well, we
four
know, yeah,
thirds.
from this we will know that y is equal
So
to,
y is just three
oh,
fourths
yeah,
x.
3/4 x. And if
So we
y
can
is
just
equal
say
to 3/4
y
x,
is 3/4 x.
then BE will be equal to 1/4 x, right? BE
Uh
will be
oh yeah.
1/4 x.
Okay, yeah. So this sums to x, and then this will just be 1/4 x. So then you can just say 1/4 of x equals the root of 16 minus x squared. So that's much easier to solve. And you can just have it as x squared.
Yeah, you can leave it as x squared because x squared is what we're looking for in the end anyway.
Yeah, we're looking for the area.
Yeah.
Okay, and then you get x squared equals 256 over 17.
That's our
And yeah.
answer. Woohoo.
Um I do want to plug this into my TI though. But we do have extraneous information here, right? Like we could set up
What
three
ex-
equations.
what extraneous information?
Like, actually, no, maybe they like inner describe themselves, so maybe it's not. Okay. Uh, it just returned false.
Mine's calculating. What the heck is this?
Did it say false?
No, it basically moved everything on the right side to the left side and set it equal to 0.
Oh, what?
And said that it was equal to 0.
Wait, are you using the solve function?
Yeah,
Wait, why were you getting different things then?
it's calculator settings maybe, I don't know.
Oh, yeah, maybe setting.
Yeah,
Okay, whatever.
whatever. Don't use
Choose.
the, don't do it like this. It's a dumb way to do it.
Yeah, that is so dumb, actually. Okay.
Notice the
Okay.
similar triangles.
Oh yeah, I used some of my triangles, but I didn't use the 4/3 on there because I'm bad. All right. Next problem. How many distinct four-letter permutations are possible using 4 of the 10 letters in math counts? Okay. So we just wanna make 4-letter permutations from 4 of the 10 letters in math counts. Okay. So we should look at our letters and look for repeatings. So if you look at all of them, actually the only repeating letters that we have are T's. So we basically have 2 T's and one of everything else. So then what? We want to make 4-letter words. And how many ways can we do that? Well, we could just look at cases. We can look at the case the case with 2 T's and one or less T's. Okay, so looking at the one or less T's, this is just saying we can't use 2 T's, right? So basically, then it's just then we just have 9 different letters to use, right? So then it's just going to be what? It's just going to be 9 choose 4 to choose the 4 letters out of the 9 that you're going to use, and then you can order them in 4 factorial ways, right? So multiply that by 4 factorial. And then this one, we're gonna have to use the 2T's. Okay, so we have to use the 2T's, so let's put them in here. Okay, so we can choose, so we have 9, or no, we have 8 other letters. So we can choose which 2 that we're gonna have in here by having A choose 2. And then we can order them, um, hmm. Okay, so we can think of the 2T's as being in front of the, or no, okay, actually, no, okay. So we can just think of this as so we're gonna have 2 other letters and we're gonna have 2 T's. So we can just think of this as like the permutations, but we have some extra letters. So that's just gonna be 4 factorial over 2 factorial. So basically, if you have permutations of like letters or whatever, and some are repeating, it's just gonna be what you would normally have 4 factorial over the number that are repeating their factorial. Okay, so like a better example would be uh what uh uh Bill
Oh, what?
Monopoly.
Oh, that's a nice name.
Okay. So what if we were just looking at permutations of this? Just like sorting this, right? So normally you would have what? How many letters? Six. No, seven. I can't count. Okay, normally you would have 7 factorial of this if none of the letters were the same, right? But some of the letters are the same. So then what you would do is for each repeating letter, you divide by how many of those letters there are factorial. So we have three L's. We're going to divide by 3 factorial. And we have two I's. We're going to divide by 2 factorial. So then that's the number of ways to arrange that. Okay, so in this case, we would just have 4 factorial over 2 factorial. So we're going to multiply this by 4 factorial over 2 factorial. And then that's all of our cases. So then we just add these. So 8 choose 2 will just be 8 times 7 over 2. And then 4 factorial over 2 factorial will just be 4 times 3. Yep. And then that'll just be 2. And then we have 56 times 6. And this will just be 33 6. Yep. And then we have 9 choose 4 times 4 factorial. So 9 choose 4 will be 9 times 8 times 7 times 6 over 4 factorial times 4 factorial. Okay, but the 4 factorials cancel. So then we have 9 times 8 times 7 times 6. Okay, so so this is what? This is 72 times 42. Okay. Um okay. All right. So then we have that, and then it's just going to be 3024, and we need to add 336. Then we have 3360. And cool, that's your answer. It finally didn't make like adding or multiplying mistakes. All right. Um. Okay. I'll work somewhere else. An equilateral triangle shares a side with a square, and a circle is inscribed between them as shown. If the radius of the circle is 9 minus 3 root 3, what is the side length of the square? Okay, let me first try to draw the diagram here. Well, the circle's a little bit too big. Alright, so the radius is 9 minus 3 root 3, and we want to find the side length of the square. Alright. So really we want to do something with the radius, obviously, because that's what we're given. So we know we're gonna have to do something with that. So we want to see how we can just do something with it, right? So really, like, what can we even like attach this to? We can put a line here, we can put a line here, and we can put a line here, right? So all these are going to be radii of the circle, and we want to try to somehow relate it with the side length of the square. And here we can see we form a square, right? So we know that this will also be the radius. So all of these will be radii. So that means let's think of the ways that we could try to find the side length of the square, right? We could try to find this length. That would work because we have the radius already here, so then we get the side length of the square. We could try to find the side length of the triangle because the triangle shares a side with the square and it's an equilateral triangle. So then this length will just be the side length of the square. You can also try to find this length, okay, or this length right here. And this will also be the radius. So we can just find this one. All right. So which one looks the most promising? Well, probably not this one, right? Because there's really nothing going on over there. And this one's also just not good. There's nothing going on there either. So we should try to do something with this side or do something with this side. All right. So what can we do here? Well, one thing we can do is draw a line from the center of the circle, down here. And then what's going to happen with this? Well, we can see that these two triangles. So okay, so we've drawn these radii down here, right? And we made them perpendicular to the sides that they've been drawn to. Um, uh, yeah, these triangles will be. Oh, actually, um, uh, you can't say they're congruent, actually, can you? I mean, you just have SSA, but that's not gonna work.
Um, you have you have two congruent angles actually,
Oh, what?
because because the line is a bisector of the bottom angle, right?
Hmm. Yeah, yeah. But
It's
like, how do you know it's a bisect? I guess you could say it's just
it's
from symmetry.
it's from the origin to the intersection of the two tangents. It's always a
Oh, okay.
bisector.
Yeah, okay. You could say that. Yeah, okay. Sure. So yeah, if you have
And also
you have two.
those two lines are also the two tangent lines are also equal length, so you can do SAS.
Yeah. Okay. So if you have two tangents to a circle, if you connect the center of the circle to the point where the tangents meets, it's always going to bisect the angle. Um, I mean, this is pretty obvious by symmetry. Um, Also what? Also just um just by symmetry. Hmm. Uh yeah, sure. I'll just say no, okay. But also the tangents are equal length, right? So you can say these are equal. If we draw this, then these are equal because they're radii. And then we know this is equal because this is the same, right? So okay. Then we know that the two triangles are congruent by SSS. So then these two angles have to be equal. So this definitely is the angle bisector. Okay, so that's exactly what we have here. These are two tangents to the circle. So then we can conclude that this will be the angle bisector of this. Also then you know that these two triangles are congruent by SAS. Uh Actually no, not by SAS. By AAS. Just by AAS. Yeah. Alright, but sure, AAS. Okay. They're congruent. That's not too helpful here. What's more helpful is the angle bisector here. So the angle on the equilateral triangle is 60 degrees. So then you know that this total angle has to be 30 degrees because this whole thing is a 90-degree angle, and then it's an angle bisector. So then you know that this is 15 degrees. And this is a right triangle, so this 15 degrees can be very useful. And we said we could find this side, right? So, okay, so sure, let's call this x. So then we can create a relation between x and r with our 15-degree right triangle here. So that's really nice. So what can we say? We can say tangent of 15 degrees equals r over x. Okay? And then what is tangent of 15 degrees? Well, Um, okay, so you can do this by using the tangent identities. So we know tangents. of a plus b equals tangent of a plus tangent of b over 1 minus tangent of a times tangent of b. Okay, and if you have tangent of a minus b, then so if you have tangent of negative negative b, sure, then this will equal the negative tangent of b, right? Because tangent of b, or negative b, will just be equal to sine of negative b over cosine of negative b, right? And if you have sine of a negative angle, it's not going to, no, if you have cosine of a negative angle, it's not going to change anything, right? Because like you can think of it on the unit circle. If you have an angle like that, this x value is its cosine, and if you have the negative, well, the cosine is going to be the same. If I can draw that correctly, which I can apparently. So yeah, the cosine will be equal. So this cosine will just be cosine b, right? And then the sine of negative b, the sign here is actually the negative of that, right? So then sine of negative b will be negative sine b. Alright, so then sine b over cosine b is negative tangent b. So yeah. So if a tangent of a negative angle is just negative of the tangent of the positive angle. Okay. So then what? We can apply this into that equation right there, just by saying like it's like tangent of a plus negative b. So everywhere where we have tangent of b, we can substitute that with negative tangent of b. So then we have this equation. All right, now we can utilize this in here, right? Because we can say tangent of 15 degrees will equal tangent of 45 degrees minus 30 degrees. And then we can put that into this equation, right? And this is easier to work with because we do know what the tangent of these special angles are, right? Yeah. Yeah, you could do it like that. Or you can do 60 degrees minus 45 degrees if you fancy that. Sure. All right, I'll just do 45 degrees minus 30 degrees. So this will be equal to tangent of 45 degrees minus tangent of 30 degrees over 1 plus tangent of 45 degrees times tangent of 30 degrees. Okay. So tangent of 45 degrees will just be equal to 1. And then tangent of 30 degrees will just be equal to 1 over root 3. You can check this on just the 30, 60, 90 triangle, or I mean, you can just do a lot of stuff. Yeah, you could say tangent of 30 degrees is sine of 30 degrees over cosine of 30 degrees. So then this is just sine of 30 degrees is just 1/2, and cosine of 30 degrees is just root 3 over 2. So then this is just 1 over root 3. So then this is just 1 over root 3. And you can rationalize it to 3 over, or sorry, what? You can rationalize it to root 3 over 3. Alright, so, okay, yeah, so then we substitute our values into there. Then we will get this. Okay, and we want to, let's put these into just like one fraction. So 1 minus root 3 will be root 3 over root 3 minus 1 over root 3. So it'll be root 3 minus 1 over root 3. And that will be root 3 plus 1 over root 3. So the over root 3's will cancel, and then we have root 3 minus 1 over root 3 plus 1. Okay, so this is equal to tangent of 15 degrees. Okay, so then we have, why do I write it so big? Then we have root 3 minus 1 over root 3 plus 1 is equal to r over x. So then we can solve for x. X equals root 3 plus 1 over root 3 minus 1 times r. And we can substitute r for 9 minus 3 root 3. There we go. Now what? Now, no, okay. Now I can just multiply that out. So yeah, sure, just multiply it out. So then you'll have 9 root 3 plus 9 minus 3 root 3 minus 9. Okay, so the 9's cancel. Oh, and this is still over root 3 minus 1. Then we have 6 root 3 over root 3 minus 1. Alright, and then that is x. So to find the whole side length, we need to add r. R is again 9 minus 3 root 3. Alright, so then this will be equal to 6 root 3 plus 9 root 3 minus 9 um minus 9 plus 3 root 3 over root 3 minus 1. Maybe I should have just, yeah, I think I should have rationalized this first. Yeah, that would have been better. See, if I rationalize this first, then I would have like something here, but then this would just be like 2. So then, yeah, that would have been a little bit faster, I think. All right. Um. So then this is 18 root 3 minus 18. So the root 3 minus 1. And we need to rationalize. So we're gonna multiply by root 3 plus 1 on top and bottom. So then on bottom we'll have 3 minus 1, and on top, kind of messy. We'll have this times root 3 plus 1. Alright, and then this is just 2, so we can get that out. By taking out a 2 from that. Alright, well, we can just take out a 9 from that. Right, and then we have just root 3 minus 1 plus times root 3 plus 1, which is just root 3, or which is just 3 minus 1, which is just 2. Alright, and then we finally get 18. Yeah, I think it would have been a lot faster if we just rationalized this first. So if we brought the root 3 plus 1, if we multiply top and bottom by root 3 plus 1, and then we have 3 plus 1 plus 2 root 3 over 2. So then we just have 2 plus root 3, right? So then we don't have any denominator stuff, and then the algebra should have been faster. All right. Oh, let's check our answer. Yeah, it's 18. All right, anything you want to say there, Bill?
I mean the rest of this stuff, just like algebra and like, so there's not really anything much to say about this. So no.
Yeah. All right, let's move on. Number 28. What is the minimum value of 8x cubed plus 36x plus 54 over x plus 27 over x cubed? Wait, do you want to show them the proof thing on this problem? Bill?
Oh, the proof of this problem?
Yeah.
Sure. I mean, I don't have my meet up though, so do you want me to just do it on here on this meet?
Wait, what?
No.
Oh, actually, it's not bad. I'll just do it.
Okay.
Okay. All right, so there are multiple ways to do this problem. Okay. If you know calculus, this problem is like extremely easy. Um, so basically,
We should do the
we have
problem first and then do the proof, I think.
what do you mean to the problem first?
Like, do the problem first and then prove the thing methods which we use to do the problem, I guess.
Wait, what?
Okay, just go. Just go. Just go. It's okay. It's okay.
Okay, we have a function. You can say it's f of x, and it's all this stuff, right? Okay, and then we're looking for the minimum. We're looking for the minimum value of this function. Okay, so if you know calculus, you know that you can take the derivative of this function, um, and the minimum will be where the derivative is equal to 0. So, slight recap if you hadn't known it, I guess. So if you have a function, um, uh, does this what does this even look like? I don't even know.
What do you mean? Like, what does what look like?
F of x, our function here. I don't know. Okay, I'll just draw something random. Okay. Uh, boom. Okay. Um. Okay. So if we this is so okay. So if this is our function, if we take the derivative of the function, we're left with another function that tells us um a function for the slopes of the function at any point x, right? But if you have a minimum, the slope at its minimum will have to be 0, right? And so will its maximums. So then if you take the derivative and set that equal to 0, you will find solutions of x where it either corresponds to a maximum or a minimum. So we can lower our x's if we just find the derivative and equal it to 0. Um, so yeah, if you know calculus, you should do that. We'll just do that right here. So it's just really easy derivative. Just apply the power rule. Um, so boom, and then this will be minus 81 over x to the fourth, and it will be equal to 0. Okay. Um, so I mean, this is not the best polynomial to solve, but um, but if you look at it, you can see that you can actually factor it by grouping. If you group these two, you have 12, sure, 12 times 2x squared plus 3. And then you can take out, what you want this to be 2x squared, right? So then you could do over x to the fourth, and this will be 27. So then this will be 2x squared, and this will be plus 3, right? So then we have two 2x squares plus 3's, and then we have just 12 minus 27 over x to the fourth times 2x squared plus 3. And this equals 0. Okay. And then what are solutions to this? Well, this right here has no real solutions when it equals 0 because x squared will be positive for all real numbers x, or non-negative actually. But then that can't equal 0, right? So then we just have to see or look at 12 minus 27 over x to the fourth equals 0. This is just 27 over x to the fourth equals 12, or 12x to the fourth equals 27, or x to the fourth equals 27 over 12, which you can take out at 3, equals 9 fourths. So then if you square root once, you'll get x squared equals 3 halves. So then if you square root one more time, you get x equals root 3 over root 2, and you can rationalize. Then you have root 6 over 2. Okay, so x equals root 6 over 2. Right. Okay, so then you found where the x values the minimum occurs, and then you can plug it in. Okay, so right, like I said, the x values of a function where its derivative equals 0 correspond to the minimum and maximums of the function, right? So we got really lucky where we only found one x value, so and that's that's going to lead to our solution. But if you had more, then what you could do, or if you have multiple x values, you could just it would take more work. You would just like plug like all of them in and see which one is the the smallest, and that will be your minimum. All right. So we just need to plug this x value into f of x. So x cubed will be 6 times root 6 over 8. Then we just have that. And we just have it like this. And this will just be the flip of that. Like this. Right, and then these 8's cancel. This will be 18. We can rationalize this, or so we can multiply top and bottom by root 6, so then we get that. Cancel these, so then we get 18 plus 18 root 6. And then this is what? We can multiply by root 6 on top and bottom again to get another 6 here and a root 6 there. So then we can take out okay, we can take out a 3 and a 2 from 27 and 8 to get 9 and 4. Take out a 3 and 2 from that again to get 3 and 2. So then 6 root 6. All right, now we just need to add all these coefficients. They're all root 6. So that's just going to be what? 48 root 6. And that's your answer right there. So this really wasn't too bad if you just knew calculus. But we'll also tell you a way where you could do it without calculus. And it's pretty cool. So if you have something like ax to the n plus b over x to the n, the minimum of this function will always be when x or when ax to the n equals b over x to the n. Okay, and so basically, like in our function, we can pair up our ax cubed plus 27 over x cubed and 36x plus 54 over x to have it like this. So you can see this in our solution here actually. You can see that these two are equal and these two are equal, right? So that's what we were saying with this. We were saying that if you had like these two, the minimum would be when they're equal and when these are equal as well. All right. So how would you use this to solve for that though? Well, what you could do is right. So you can pair them up, pair these two up, and pair these two up, and then you can say the minimum of this happens when ax oh okay, sorry. You can say that the minimum of this happens when ax cubed equals 27 over x cubed. And this will just be when x to the 6th equals 27 over 8. And 27 over 8 is just 3 over 2 cubed, right? So then this is saying x equals root 3 over root 2 on this minimum. So this is minimized when x equals root 3 over root 2. Okay, and then we should also look at when this is minimized. So this is minimized by our thing when they equal each other. So then it's saying this is minimized when x squared equals 54 over 36. You could take out a 9 from top and bottom to get 6 over 4, and you could take out a 2 to get 3 over 2. Okay, so then you get x equals root 3 over root 2 when you minimize that. Okay, so basically, if you apply that here, you can see that both of these are minimized when x equals root 3 over root 2. So then the sum of this would obviously have to be minimized when x equals root 3 over root 2. So then you can just put that into the function, and you'll get the same answer that we got before. If you don't get the same x value for these when they are minimized, it will be harder. Then I'm not really sure how to do it without calculus. Then it would be kind of hard. Yeah. All right, and then I'll just briefly prove I'll briefly prove why this works with calculus. It's pretty easy. So basically, we're looking for the minimum value of this function, right? So again, that's going to happen when the derivative of this function equals 0. So let's take the derivative of it. So the derivative will be this, and it's minimized when this equals 0. Um, and oh yeah, so this function this function only has like one time where its derivative equals 0, and that's where its minimum is. So then you can apply this. Yeah. All right, whatever. So, oh, whoops. There should be a n here. Yeah. Okay. So then, just solve for x. Or no, okay. Or you don't have to solve for x. You can just do it. Okay. So move that to the other side. You can cancel out the n's. So then we have a times x to the n minus 1 equals b over x to the n plus 1. And then you can multiply by x on both sides. And then you'll get a times x to the n equals b over x to the n. Okay, so then this is exactly what we said before, right? So this is minimized when a times x to the n equals b over x to the n, basically when these components are equal to each other. Okay. Yeah, that's it. So what's the takeaway from this problem? It's that if you're looking for the minimum of like something to the power and the something like over to the something to the power, it's minimized when those two things equal each other. Also another thing is just to maybe like study calculus. That might help you in a lot of stuff. Calculus is pretty good. All right. Anything else you want to say, though?
Yeah. So the whole like thing where it's tangent at the they have the same slope at the intersection. If you put it on a graph, it's pretty easy to see that. That's pretty easy to see if you put it on a graph. So if you're ever curious about that, you can just graph like two equations and then just look for yourself. It's pretty obvious.
All right. All right. Let's move on. Number 29. One box contains 4 green balls and 3 red balls. Another box contains 4 red balls and 3 purple balls. A box will be selected at random. Then 2 balls will be randomly selected from that box without replacement. If the first ball is red, what is the probability that the second ball will also be red? Express your answer as a common fraction. All right. So we have 2 boxes. A box will be selected at random, and then we're going to select 2 balls out of that box. And we're given that the first ball will be red. And then we want to find what's the probability that the second ball will also be red. Okay, so what we have to do here is we want to find the probabilities that lead up to our given. Or we should find the probability of choosing the boxes that will lead up to our given. And then we can use that information to find the probabilities of the boxes when we're given this condition. So right, okay. So like what if we choose the first box? Then what's the probability that our first ball is going to be chosen as a red ball? Well, it's just going to be 3/7, right? And the other box is just going to be 4/7, right? So if we're given that the first ball is red, then these will be the probabilities for the boxes. Um, these will be the probabilities of the boxes. So yeah, if we have it as given red. Um, if if this was like higher, then we would have to like set a proportion. Or like if like we needed these to sum to one. If they did not sum to one, then we would have to like scale them down by the same factor. Um um Also this works because the boxes had equal probability of being selected. If they didn't, then we would have to modify it a bit. Um, what would you have to say? We had to look at it more in detail, kind of. Yeah. So like, hmm, yeah. All right, but whatever. Yeah, it's fine. Okay. So we can do this because the boxes have equal probability of being selected, and these also sum to one, so we can just leave it as that. So the probability that the first box will be selected is 3/7, and the probability that the second box will be selected is 4/7 because of our given. All right, and then what's the probability that the second ball will be selected in these? Well, this one will just be 2/6, and this one will just be 3/6. So then this is just 1/7, and this is just 2/7. So then you just add these, and that's just 3/7. And yeah, that's your answer. Hmm. Um. Also, wasn't there an equation for like probability of like p given a equals
I think there is, yes. Let's
probability
see.
of b and a
I
over
remember doing
probability
that
of
at
a?
some point, but
I think that's pretty useful. I'm gonna look it up. Oh, okay, yeah. Oh,
it
yeah,
makes
I
sense that
got it
it's
right.
PBNA over P over PA. It makes sense that it's that.
Yeah, yeah. This is the equation for it. Yeah, this is pretty useful. So the probability of B given A will be the probability of B and A over the probability of A. I mean that kind of just makes sense, right? It's like you're given A and so you're really looking at the probability of B and A because you were given A, but you also had to divide by the probability of A because you were already given A. All right, yeah. So okay, maybe we can apply this to here. So what? We want to find the probability of second red given first red, right? So this will be equal to the probability of first red and second red over the probability of just the first red. Hmm. The probability of first red and second red. Okay. Okay. So probability of first red and second red. That will just be so we have 1/2 for the boxes. We're just like going through it now. And then the first red will be 3/7, and the second red will be 1/3, like that. And this one will be 4/7, and it will be 1/2. Okay, so then this will be 1/7, and this will be 1/14. So then we just add these. So then this is just 3/14. Right, so probability of first red and second red is 3/14. And what is probability of first red? Well, we're just gonna have the 1/2 again. Well, we're gonna have this except without the 1/3 and 1/2, right? So like that, like that. And then you just do that, and you just need to add them together. If I did this right. Right? This will just be what? This will just be 4/14. So this is 7/14, or it's just 1/2. Alright. So this was probability of first red and second red, and this was probability of first red. So then probability of second red given first red is 3/14 over 1/2. And this is again 3/7. Very cool. So yeah, maybe that is a more methodical way to do it. But yeah, this is a really good formula to know, I guess. Anything you want to
I
add,
mean,
Bill?
just like logic in general, it's good to know. Just logic,
Yes.
stuff like that. I mean, this problem ends up being fairly simple, so there's nothing really to say about it.
All right.
It's just that it's easy. It's gonna be easy to trip you up, like when you're doing it.
All right. And our last problem. A solid right circular cone has radius 5 centimeters and 12 centimeters as shown. What is the probability that a randomly chosen point inside this cone is a distance of at least 1 centimeter away from the closest point on the surface of the cone? Express your answer as a decimal to the nearest thousandth. All right, so we have a cone. And what's happening here is we choose a point inside the cone. Boom. And we want to see the probability that it's farther than 1 centimeter away from anywhere on the cone. Okay, so how can we think about this? Well, we could think about this as there are like 1 centimeter projections from all everywhere on the cone, right? And you can't be within these 1 centimeter projections, right? Okay, yeah, so it's everywhere. All right. And then this is so you can't be like within here, and you have to be like somewhere here, right? And this will form like a new cone shape, right? So then basically the probability of this happening will be the volume of the new cone shape over the volume of the old cone shape. Um that's just like probability by volumes and stuff. I don't know. That should be pretty intuitive. All right, but how are we going to do this though? Well, we need to find the volume of this new cone, and the volume of the old cone is pretty easy because we already have the height and the radius. So we really just need to find what this new cone is like. All right. For this new cone, we need to find its new height and its new radius. What we can first do is we can first push up this circle up by 1 centimeter. So essentially, we're doing the projections of this circle first. So we're going to move it up by 1 centimeter. We moved it up by 1 centimeter. And it's still gonna have to be within the cone, right? So we're gonna still put it within the cone like that. Okay, so what happens if we put it up 1 centimeter? Then this height will be 11 centimeters. And what will the new radius be? Um, well, we still have the original cone shape, right? It stays the same. I mean, you can think of it as like similar triangles, right? Um, like the ratio of the sides are still going to be the same because we just have like a slightly scaled down version of our original cone, right? And yeah, you can just all see it in similar triangles. This angle is the same, and this angle is still a right angle. So those two triangles are going to be similar. Okay, so then what? Then this new radius will be 5 times 11/12, which is 55/12. Okay. Now, is this our final new cone? Well, it's definitely not, right? Because we only did the projections of the circle. Now what we need to do is to do the projections of the sides. And this is going to be weirder, right? The projections of the sides are going to be like on a right angle and of a distance of 1 centimeter, right? So it's going to look like that. Um, right, it's going to look like that. Okay, so what is our new radius going to be? Or what is our new circle even going to be, right? Well, it's going to be where the 1 centimeter line from here just touches the circle, and where it touches the circle will be the new radius of the circle. So it'll be slightly smaller like that. And where it touches, going to the center, that will be the new radius. And this has to be um a point coming from a right angle through 1 centimeter. It can't be less or more than 1 centimeter. Okay, so let's think through this a little bit. Why can't it be more than 1 centimeter? Well, that's pretty obvious because our extensions are only 1 centimeter long, right? Now, why don't we want it to be less than 1 centimeter? Well, then the radius is gonna be bigger than what it's actually supposed to be, right? Basically, this 1 centimeter gives us the largest, or gives us the smallest radius that we can have, right? Um, and yeah, and why do we do it at right angle projections? Well, that's what it's saying by 1 centimeter away from stuff, right? If you're looking at 1 centimeter away from like a line, it's just the distance from that point to the line at a right angle. All right. So so what? So what I said was our new radius will be the radius when we have it like this. Well, this will be the new radius, and this will be 1 centimeter, and this will be a right angle. I did not draw it very well there. Yeah. So we need to find what this new radius is. Okay. So how are we going to do this? Well, one thing we can do is we can find the slope of this cone, right? This is still like the same stuff as our original cone. And the slope of our original cone, like here, is just 12/5, right? It goes 5 there and it goes up 12. So its slope is 12/5. Now this makes a right angle with this side of the cone, which has a slope of 12/5, right? Which means that this will have the negative reciprocal of this slope. So this slope will be negative 5 half, or sorry, negative 5 over 12. All right. So then what can we do? Then we can draw a triangle right here, a right triangle. Actually, that's not. this right triangle, if you put it down, it won't go to the edge of the circle. The edge of the circle will be touching like all the way there. And this going down will not touch the edge of the circle at all. All right. So what we can do here is we can label this as x. Okay? And we know the slope is negative 5/12, right? So then this has to be, or sorry, not negative. This will be 5/12 x. That side right there, right? Okay, and then this right triangle, we can see that it is a 5, 12, 13 triangle, right? Um, so yeah, or we can say we can instead say that this is 5x and this is 12x. Okay. So then we have a clear 5, 12, 13 triangle, and we could see that x will be equal to 113 from this being 13x. So x will be equal to 1/13. Okay. All right. So if x is equal to 1/13, then we know the length of that, right? The length of that is 12/13. So now all we have to do is find the length of this. If we find the length of this, and we have the length of this, then we can find the new radius by subtracting our old radius by this and that, right? Now, how can we find this? Well, we can just use the slope of the cone, right? The slope of the cone is 12/5. And that right there is 5x, right? And x was 1/13, so this is 5/13. So then what is the side length of the cone? It's gonna, or sorry, what is that length? It's gonna be 25/12, right? So that when it's multiplied by the slope, oh wait, what? 25/12. No,
You should just
25
use the
over
big.
12
You
times
you should
13.
just use the big triangle instead of using those small
I don't
triangles.
care. Okay, sure, maybe. I don't know.
That's so much
It
less
doesn't matter
work.
too much. It's not that much less work.
It really is though.
Not really. Okay, sure, maybe. I don't know. It's whatever. Okay, so this will be 25/12 times 13. So that if you multiply by the slope, you will get 5/13, right? All right. So then we have these lengths. Okay, and then we can find our new radius now. Our old radius right there was 55/12. So our new radius will be this minus 12/13 minus 25/12 times 13. So this will be 55 times 13 minus 12 times 12 minus 25/12 times 13. Okay, this will be 55 times 13. So that's just 143 times 5, which is just 517. So it's going to be 715 minus 144 minus 25/12 times 13. Then this is 690 minus 144, which will be 546 for 12 times 13. Um, and then you can cancel out a 6. So then you'll be left with 91/2 times 13. Wait, that doesn't look right. Didn't we simplify it to like, what
Yeah,
was it? Oh no,
we
I did
simplified
more.
it to we simplified it more than this.
No, yeah, it was like something really nice.
Yeah, it was 13 12,
Oh,
12 13, one of those. 13 12, I think. You sh
What did I do wrong here?
Should have used the big triangle.
No, no, no. Okay, these values are correct. It was just some error right here. Come on. Alright, 143. Yes, that should be 715. And then we minus those, right? Alright. See, 715 minus 25, 690. And then we subtract 144. So that's going to be 10, 6, 4, 5. See, is that not 546? And then you take out a 6. Then it's 91 over 2 times 13? What? What is wrong here?
You should have used the big triangle.
Yeah, something's wrong here. What? What? What is going on? Oh, wait. No, this is totally correct. No, we just didn't think it was correct. This is correct. And then you take away a 13 from 91, which will be 7.
Did we just
And you get 7
simplify
halves.
at?
No,
Did
yeah,
we
the new
just
radius is 7
did we
halves.
just fail at simplifying?
What?
Oh no, okay, never mind.
No, yeah, this is the right answer. I was like, where did we go wrong? But yeah, it is 7 halves. All right. Okay, the new radius is 7 halves. There we go. Okay. Now we need to find the new height, right? Um, okay, so now let's zoom in on the height. So we got the height there, and we've got more right angle 1 centimeter people, right? Okay, so again, we're gonna look for the new height that where we're gonna subtract like this much. And this is where it's going to be another right angle meets this, and it has a 1 centimeter length. So, you might think like, isn't the height just going to be -1 from there because like you just have a 1 thing from there? But this will be, if you extend this, this will take out like more than this 1, right? Like you can just see this in a triangle. This is a right triangle, right? So this hypotenuse has to be more than this 1, which means that this will definitely take out more length than this 1 will. So you should use this one, the maximum length it takes out, not the one that comes from there, right? Right? It's like if you shade in this, it's gonna look like that. And then it takes out way more than that 1. All right. Okay, so kind of need to do the same thing again. Um, yeah, what? Yeah, this has a slope of 12 fifths, and this will have a slope of negative 5/12. And then you can do this on a lot of ways. Um,
Use the triangle that's already there.
okay, sure, Bill. So we can just use this triangle. This will be a 5, 12, 13 triangle. Um, I mean, you could just see that from the slopes. I mean, you can also do it, and you can also make like a triangle here. See from the slopes that it's 5, 12, 13, and then
Also
and then
notice the
this triangle is
angles.
similar to that triangle.
Yeah, just
Also,
notice
what?
the angles.
Sure,
It's similar by similarity, whatever.
sure. Okay. So yeah, this triangle is a 5, 12, 13 triangle. So this is one. So this corresponds to the 5 side. So this will be um, what, 12 fifths, and this will be 13 fifths. All right, yeah, so that's really easy. Then this is just 13 fifths. So then we had 11, so we need to minus 13 fifths from that. Then this will just be this 42 fifths. All right, now we finally got it. Our new radius is 7 halves. Our new height is 42 fifths. All right, so our old radius was 5 and our new radius, or sorry, our old radius was 5 and our old height was 12. Okay. We want to find the ratio of the volume of the new cone to the old cone. So that's going to be this squared and times this over this squared times this. Um, to find the actual volume of the cone, you would have a 1/3 and a pi here, but you have that on both top and bottom, so they cancel out. So we're just finding this. All right, so what is this? Let's find out. So we can take out a 7 from the 42. Then we have 7 cubed. And then we have 6. And then we have 2 times 5 cubed times 12. Now, well, you can take out a 6 from the 12 and a 6 from there. Oh, oh yeah, that is a 2 squared. This should be 2 squared. So then this is 7 cubed over 2 cubed times 5 cubed. Want to express your answer as a decimal to the nearest thousand? This 2 cubed times 5 cubed is 1,000, right? So then this is just 7 cubed over 1,000. So then it's just 0.343, where 343 is 7 cubed. So yeah, that's your answer. And that is the answer here as well. All right, cool. We're pretty past time now. So that's gonna be it. Um yeah, we finished 2015 National Sprint today. Uh we won't have a meeting next week because of Thanksgiving. But we will have, or we're planning to still have a meeting the week after that, and the weeks after that to come. And so the week after, or the next meeting that we will have, um, we will start with 2015 national target and try to get through as much of 2015 as we can. All right, thanks for coming, and let us know if you have any questions. And yeah, thank you. Goodbye.